Okay, let's take a look at a few examples from 3.6. Let's start off with number 6 maybe. This is a little bit more difficult one. I think you might be able to handle number 4 on your own. Remember on number 4, when you have a c on the right side, that just represents any constant, and the derivative of that is going to be 0. Let's take a look at number 6. We have y to the 5th plus x squared y cubed equals 1 plus y to the x squared. Now we're going to be using the product rule, the quotient rule, all in terms of using implicit differentiation. Now remember, we're implicitly thinking of y as some function of x that'll make this equation true, but we're not going to solve for y. This one would be very difficult, if not impossible, to solve for y as a function completely of x. So alright, so we have, we're going to use the chain rule right off the bat here. Y to the 5th, the derivative of that is 5 times y to the 4th times the derivative of what's inside. The inside function is y. The derivative of that is dy dx. Alright, so far so good. Next term we have two functions multiplied together, two terms multiplied together, and so we're going to use the product rule there. Let's take the first times the derivative of the second. Well, the derivative of y cubed is 3y squared times the derivative of what's inside, which is y. That's dy dx. So there's first times the derivative of the second. Had to use the chain rule for implicit differentiation when we took y, derivative of y cubed, plus the second, which is y cubed, times the derivative of the first. That's just 2x. Alright, so far so good. Now on the right side, well, the derivative of 1, that's a constant, that's 0. Now the next term, we have two functions again. Two functions multiplied together, so we're going to use the product rule. We'll take the first, which is y, times the derivative of the second. Remember, e stands for easy, so derivative of e to a power is just the same thing times the derivative of the exponent. Derivative of x squared is 2x. So there's first times the derivative of the second plus the second function, e to the x squared, times the derivative of the first. And the derivative of y is dy dx, because y is a function of x. Okay, so now we have to solve this for dy dx, which isn't going to be too terribly bad. What I want to do is, first of all, get all my terms that have a dy dx on the left side and all my terms without a dy dx on the right side. So terms with dy dx is this one, and this one. Terms without a dy dx are these two, looks like. Okay, so let's see. If I subtract this one over, we're going to have, so we have 5y to the 4th dy dx plus 3x squared y squared, that's that term right there, dy dx. And then I'm going to bring this term over here, so minus e to the x squared dy dx. All is equal to, on the right side, we're going to move just this term over. And so we'll have let's write this as 2xy e to the x squared, that's that term, and then this term here brought over to the right will be subtracting a 2xy cubed. So there's that term there. Okay, now I'm going to factor a dy dx out of all three terms here on the left side. Since I have all terms with dy dx, that leaves me with 5y to the 4th plus 3x squared y squared minus e to the x squared. All that is equal to 2xy e to the x squared minus 2xy to the 3rd. And finally then, to get dy dx by itself, I'm just going to divide by this multiple quantity here. So dy dx is going to be 2xy e to the x squared minus 2xy cubed, all divided by 5y to the 4th plus 3x squared y squared minus e to the x squared. And there you have it. There's dy dx. So this is a formula then, ugly formula, but a formula nonetheless. That'll tell you the slope of the line tangent to any point on the curve given by this equation, y to the 5th plus x squared y cubed equals 1 plus y e to the x squared. Alright, let's try a couple more here from this section. Let's look at number 8, where we're given 1 plus x equals the sine of x y squared. And again, we're thinking of y as a function of x here. So let's go ahead and take the derivative. Derivative of 1 is 0. Derivative of x is 1, because that's just, again, a linear term there, coefficient of 1. On the right side, we have, the derivative of sine of something is the cosine of that same thing times the derivative of what's inside. So the chain rule there. Well, the derivative of what's inside is two functions multiplied together. So we're going to have the first times the derivative of the second. Derivative of y squared is 2y times the derivative of y, which is dy dx. First times derivative of the second plus the second, which is y squared, times the derivative of the first, which is x, which is just 1. Derivative of x is 1. Okay, so we got to solve for dy dx, but notice that dy dx is stuck right here. So the first thing we're going to have to do is distribute that cosine of xy squared. We have just a 1 on the left side. On the right side we have, let's see, x 2xy times the cosine of xy squared dy dx. So that's from this first term here in the parentheses multiplied by cosine of xy squared plus y squared cosine of xy squared. Alright, so not too hard to solve for dy dx. Now I'm just going to subtract this y squared cosine of xy squared from both sides. That is equal to 2xy cosine of xy squared times dy dx. And now I can just divide by the coefficient of dy dx here. And we have dy dx on the right is equal to 1 minus y squared cosine of xy squared, all of that divided by 2xy cosine of xy squared. So again, it's kind of an ugly formula, but it is a formula. If you know the ordered pair of a point on your graph given by this equation 1 plus x equals sine of xy squared, you can find the slope of the line tangent to the curve at that point by putting in the x-coordinate for x, the y-coordinate for y, in this formula for dy dx. Alright, and then let's take a look at number 16 then, where we want to find the equation of a line tangent to a curve at a given point. So 16, we have x squared plus 2xy minus y squared and plus x equals 2. We want to again find the equation of the line tangent at to this curve at the point 1, 2. So you can notice, first of all, if you put a 1 in for x and a 2 in for y, this equation will be true. So the first thing we want to do is we want to find dy dx. So we can get the slope of our line tangent, and we're going to do that using implicit differentiation. And the reason we're doing that, again, is because we don't have y solved directly as a function of x. Y is a part of our equation. And, it's possible in some of these it's easy to solve for y in terms of x, but in most cases it's just going to be easier to just use implicit differentiation. So let's go through our equation here. Derivative of x squared is 2x. Alright, 2xy, we can think of this as a product rule. First function 2x, second function y, so we'll have the first, which is 2x, times the derivative of the second. Derivative of y, we're writing as dy dx, plus the second, which is y, times the derivative of the first. Derivative of 2x is just that coefficient of 2. Alright, next term is a negative y squared, so the derivative of that is going to be negative 2y times the derivative of the inside function, which is y as a function of x. That's dy dx. Alright, on to the next term. Derivative of x is just 1. And on the right side, the derivative of a constant, no matter what that constant is 0. Alright, we're solving for dy dx then. We have 2x dy dx minus 2y dy dx. So I've got those terms, kept those on the left side, these two terms here with the dy dx in them. And then this one, and this one we'll throw over to the right side. So that's all going to be equal to then, looks like a negative 2x minus 2y minus 1. So factoring out a dy dx from the left, we are left with a 2x minus 2y, and that equals a negative 2x minus 2y minus 1. And so dy dx is equal to negative 2x minus 2y minus 1 over 2x minus 2y. Now this gives us the slope of the line tangent to the curve at the point we're given of 1, 2. And so let's go ahead and find our slope then. Our slope is going to be m, which is going to be dy dx evaluated at the point 1, 2, which is going to be equal to negative 2 times 1 minus 2 times 2 minus 1 divided by 2 times 1 minus 2 times 2. So again, we're just putting a 1 in for x and a 2 in for y wherever we see those variables in our dy dx formula. I think everything's right there. Okay, so what do we get then? We get that our slope m is equal to, again, dy dx evaluated at the point 1, 2, which is going to be, looks like negative 2 minus 4 minus 1 divided by 2 minus 4. And so negative 2 minus 4, that's negative 6. Negative 7 over 2 minus 4 is negative 2 is a positive 7 halves. Alright, so we want a line then that goes through the point 1, 2 with a slope of a positive 7 halves. So let's go ahead and let's use We'll use y equals mx plus b form on this one. So y is equal to 2 equals our slope m of 7 halves times x, which is 1 plus b. We want to solve this for b to find the equation of our line. So it looks like 2 minus 7 halves will be b. We can write 2 as 4 halves. So b is a negative 3 halves. And so the equation of our line then is y equals 7 halves x minus 3 halves. Let's go ahead and see if we can put this in. So we're going to first graph the equation, the implicit equation of x squared plus 2xy plus minus y squared plus x equals 2. Let's do that. So we'll go to implicit here, and let's see if we can remember what that was. It was x squared plus 2xy minus y squared plus x equals 2. Alright, so there it is, and you can see it does go through the point 1 comma 2. That's this point right here. Now what we want to do is put in our explicit equation for our line tangent at the point 1 comma 2, and we said that was going to be 7 halves x minus 3 halves, I think. Let's see. Hey, there it is. You can see it is tangent to the graph at the point 1 comma 2 and touches the graph at that particular point. So we must have done something right there. Let's look at a couple more examples here. Let's start with number 19, where we want to find the same thing as we did in 16. Equation of a line tangent to a curve at a particular point. 2 times the quantity x squared plus y squared squared. We want that to equal 25 times the quantity x squared minus y squared. And we're looking here at the point 3 comma 1. So this is a lemniscate when you draw it out. Looks like the infinity sign there, number 19. But again, what we're trying to do is we are trying to find the equation of line tangent at the point 3 comma 1. So we're going to need to find dy dx. So let's go ahead and do that using implicit differentiation. And when we do that, let's see, we're going to have, we have a chain rule here. We have a function raised to the second power. So I'm going to bring that 2 down in front. That'll make it a 2 times 2 or 4 times x squared plus y squared to the first power, now times the derivative of what's inside. Well, the derivative of x squared is 2x. The derivative of y squared is 2y times the derivative of y, because again we're thinking of y as a function of x. So there's the left side of our equation. How about the right side of our equation? Well, we just have 25 times the derivative of what's inside the parentheses. Derivative of x squared is 2x, and again the derivative of y squared is 2y dy dx. Alright, so we're going to try and solve this then for dy dx. The first thing we'll need to do is to get this dy dx out in the open, we'll need to multiply these two quantities together. So we're going to have an x, actually let's do, let's take the 4 through here first. So we have 4x squared plus 4y squared times 2x plus 2y dy dx. And on the right side, I'll distribute the 25 through, so that gives me 50x minus 50y dy dx. Alright, now I'm going to have to FOIL this out. So 2x times 4x is 8x cubed. Let's see, do the outer. So 2y times 4x squared is 8x squared y, and then times dy dx. The inner is going to be a 2x times 4y squared is an 8xy squared, and the last is going to be a 2y times 4y squared. That's 8y cubed dy dx. On the right side, we have 50x minus 50y dy dx. Alright, so put all dy dx terms on the left, or non-dy dx terms on the right, and we'll have 8x squared y dy dx plus 8y cubed dy dx plus 50y dy dx. Alright, so those were 3 terms with the dy dx in them. They're on the left side now. I had to make this one positive when I subtracted over. And then the non-dy dx terms will be on the right side. So we're going to have a 50x minus an 8x cubed minus an 8xy squared. So now factoring a dy dx out, we get 8x squared y plus 8y cubed plus 50y is equal to 50x minus 8x cubed minus 8xy squared. And so finally then solving for dy dx by dividing both sides by this quantity here, we get the dy dx is equal to 50x minus 8x cubed minus 8xy squared, all divided by 8x squared plus 8y cubed plus 50y. So our slope then of our line tangent is going to be dy dx, evaluated at our point of 3, 1, which is going to be 50 times 3 minus 8 times 3 cubed minus 8 times 3 times 1 squared, all divided by 8 times 3 squared plus 8 times 1 cubed plus 50 times 1. So that's 150 minus 8 times 3 is 8 times 3 cubed. 3 cubed is 27. Minus 8 times 3 is 24. All divided by 8 times 9 plus 8 plus 50. And I think if my calculations are right, this gives us negative 90 over 130, or negative 9 over 13. So there's the slope of the line tangent. I'll let you leave it from there to find the slope, or find the equation of the line that has this slope and goes to the point 3, 1. Remember, that's the point you are going to go through the point 3, 1, and this again is our slope here of negative 9/13. Okay, we'll look at just a couple more problems in third video, an unprecedented, unheard of third video.